All right. Wrong piece of paper. All right. Right piece of paper. Greetings, Earth and space explorers. Hold on. I got to admit somebody. All right. Trying again. Greetings, Earth and space explorers. Welcome to Doc Waller's Earth and Space Report for Friday, February 28th, 2025, the last day of this short month. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a cool and cloudy evening here in my hometown of Rockport, Massachusetts. These Earth and space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining biosphere, and who wonder about the greater cosmos and all that it has fostered throughout space and time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, myriad Earth and space scientists, educators, and communicators, far-flung friends, family, and other curious folk. Thank you for your active participation and encouragements. This evening, we will explore the molecular universe with Dr. Charles Law, who will provide an astrochemical view of the cosmos. Charles is a postdoctoral researcher and NASA Sagan Fellow at the University of Virginia, having previously completed both his undergraduate studies and PhD in astrophysics at Harvard University. His research focuses on the chemistry of star and planet formation. He uses observations from radio telescopes, such as the Atacama Large Millimeter Submillimeter Array, otherwise known as ALMA, to characterize the chemical environments in which young planets are forming. These protoplanetary disks contain rich brews of complex molecules that can be studied in great detail at radio wavelengths. So let's get going. The Zoom platform is all yours, Charles.
All right. Well, thank you very much for that introduction. And thank you to everybody for being here tonight. And so I want to tell you a little bit about the molecular side of the cosmos. And so this is a field that is broadly called astrochemistry. So astro, as in studying space, and chemistry as we understand it. So this is a field that you may not necessarily have exposure to or have heard of before. So I just want to start out by defining what is astrochemistry. So if you go out and you look up a textbook definition of astrochemistry, you'll see something like this. It's the study of the formation, destruction, and behavior of molecules throughout astronomical environments and how we can use them to learn about the structure and evolution of those objects. That includes stars, galaxies, and essentially everything is in some way related to molecular astrophysics. The main takeaway, though, from this is it is molecules. It is using molecules to learn something about our place in the cosmos. So I'd like to start out talks about astrochemistry by really trying to motivate why we should care at all that there's molecules out there in space. And I think one distillation of this idea is shown here in this very nice artist's rendition, where it's of a very beautiful spiral galaxy. But then as you look close, the nearest spiral arm here turns into the double helix structure of DNA, just underscoring this connection that we have with space, with the cosmos. This is where we come from. So a lot of the questions that we can answer with the astrochemistry and molecules out in space are these questions of origins. How do we come to be? How does life come to be? And that really is the first and most important question that I like to think about. Really, how did we get here? By understanding the chemical ingredients, and if they're present out there in space, this lets us understand how we came about, but also if life is likely to be present in other environments around other planets, other solar systems out there in our galaxy and beyond. So here's just one possible way that you could go about understanding this. I study personally these protoplanetary disks, that is the swirling gas and dust around young stars. So one idea for how we got life on our own planet is that you have these prebiotic molecules in this protoplanetary nebula from which the Earth and all the planets formed. All of those molecules got sequestered into comets. And then when those comets come close to the Earth, they heat up and they deposit all those prebiotic materials onto an early Earth. That is just one such possible way in which you can trace the origin of life back to the initial chemical ingredients at the time of formation. But say you don't care about that, right? So maybe the origins is not the most, exciting question. What we can also do is understand physics by using these molecular probes. It turns out if we choose the right molecules to look at, we can understand something about the underlying physics. Here is a real image taken with a radio telescope of a nearby spiral galaxy. But now what we're actually looking at is emission from a carbon monoxide molecule. So we're actually doing a molecular mapping of an entire galaxy. This isn't stars, this isn't dust, this is actually the molecules themselves emitting. And it actually very nicely traces out the structure of this spiral galaxy. And this is just one such example where we can use a molecule to learn about physics going on in these galaxies, where the spiral arms actually are, what is the temperature of the gas, where is the gas. But it's not just these. As I said, molecular astrophysics touches all types of science. We can understand planet-forming disks, which is my personal area. We can use molecules to understand the composition of comets. We can use them to actually map out the spiral structure of our galaxy and other galaxies, as I had just shown in that image. We can use this to understand the composition of molecular clouds. We can understand the other stage. So stars form from molecular clouds, but then they die and explode, and we can understand the explosion and this process of stellar death also from using molecules. So really molecules is this thread that we can go from the very formation and the very death of stars, as well as to how do we arrive at life. So really, this is just a connecting thread. It's a tool that we use throughout all of astrophysics to tell us something. Most of what I'm going to be talking today about is in the interstellar medium. So it's what's shown here on the right half of this plot. So essentially, all of the heliosphere, that is all of the region that is influenced by the sun. There definitely is astrochemistry that you can do. You can go look at comets, you can look at the other solar system bodies, and they are rich in molecules. But today I really want to focus on the regions beyond our own solar system. That is out there in interstellar space, in the so-called interstellar medium, beyond the sun's influence. This interstellar medium is just a fancy word for all of the stuff that exists between stars. It is all of the matter and the radiation that is out there between stars far away from us. The vast majority of the ISM, the interstellar medium, is in the form of gas. Nearly 99% of it is gas in some form or the other, with a very small amount of interstellar dust, around 1%. So we have a lot of gas, so that really helps us to try to actually have some, look for some molecules, look for some interesting chemistry. I hope to convince you a little bit later on that 1% of dust actually does matter as well. So it's really both of these things working together does matter. But that's perhaps paints maybe a simple picture of what the ISM is. It is actually quite complex when you look in detail. And it is something we like to call multi-phase. That is the gas that is out there often is in different types of gas. You have ionized gas, you have atomic gas, and then you have molecular gas. And all of this depends in detail on the particular environment you're looking at, how hot it is, how much radiation is around. And what's more is that this multi-phase behavior often is happening in relatively small regions. So just to illustrate that, here's an image of the Orion Nebula taken with Hubble. And if you look here, you can see the dark dust lanes. You can see young, massive stars that are putting out tons of UV light and radiation, and charged particles flying everywhere. And then right next to that, you have a bunch of dense gas. So we have ionized gas, dense gas, all of this going on in a relatively small area, astrophysically speaking. And to really drive this point home, if we just zoom in on this central region around the most massive young stars in Orion, what we can see is a really beautiful image. Again, this was an actual image taken with JWST, the James Webb Space Telescope, and we can actually see this transition. In orange here, this is the molecular gas. That is the gas that is dense enough to actually have formed molecules. The blue here is all ionized gas. And what you can very clearly see is that there's this transition zone. You go from this blue material here, which is the ionized gas, to the orange, which is the molecular, and there's an ionization front that is moving along, that is ionizing all the molecular material with time. And why this is happening is because you actually have massive stars sitting right here, and they're pumping a ton of ultraviolet, high energy radiation in this direction, creating this moving and propagating ionization front that will just continue to evolve as that radiation breaks in and destroys more and more of the molecular material. So that is all to say the interstellar medium is dynamic and multi-phase and quite complex if we zoom in. The overall composition of this gas, taken broadly, is mostly hydrogen and helium. So over 90% hydrogen, a little less than 10% helium, and then around only 1% of heavier elements. And here's a jargon thing that comes up a lot for astronomers is that all of these heavier elements we call metals, which doesn't make sense for your normal perspective because we're calling things like nitrogen, carbon, oxygen metals just because they're so rare. That doesn't really jive with your normal expectation of what a metal is, but this is just because almost everything is hydrogen and helium. So anything is not that, the folks have just started calling metals. All of this is really set by the Big Bang. The fact that you have so much hydrogen and so much helium that's left over is a byproduct of Big Bang nucleosynthesis. But the metals themselves, these are from enrichments due to stellar evolution, stellar explosions that get ejected back into the interstellar medium. And so if we actually take a census of all the different elements in the periodic table, we can color them by their origin. And if you look at hydrogen and helium in blue, they're coming from the Big Bang. That's where most of the stuff comes from. But if you look at some of the other colors here, what you can see is that there's a few different ways to make elements. They're often very energetic, such as emerging neutron stars, exploding white dwarfs, exploding massive stars. It really takes these really energetic events as crucibles to make these heavier elements. And in particular, the vast majority of elements that we care about and that we're more familiar with, essentially those first couple rows on the periodic table, are mostly coming from exploding massive stars. How this works, just very quickly, is that you fuse these heavier elements in the cores of massive stars throughout their life. And so we often hear that this is just a process that happens in the very core of a massive star, something that's many times 8, 10, or more times the mass of our sun. But it actually looks like an onion in detail. You have successive layers of this fusion happening. The densest parts of the star right in the center here, you're forming iron. But as you move out, you're forming progressively lighter elements so that you have an onion going from hydrogen, helium, carbon, oxygen, magnesium down to iron here in your star. And this is what's happening throughout its life. You're making these onion-like layers. You're going from lighter elements to heavier elements. But as you all know, what ends up happening at the end of the life of a very massive star is that it explodes in terms of a supernova. Supernova we can observe. Here's a very famous supernova remnant that we can observe in our own galaxy called Cassiopeia A. And you're seeing the ejected material from the once massive star. But what's really nice about having observations like this is we can see this process of heavier elements being formed in the star and then being ejected in the supernova. So here, each color corresponds to an X-ray image, a slice in X-rays of different elements, colored here red, green, blue. You can see that each one of these heavier elements is actually just being ejected back into space. So they're made in the centers and layers of massive stars. Supernova explosions happen, and those heavier elements are then put back out into space. And essentially, it is these ingredients that we need to form interesting chemistry. And perhaps more importantly, that these are the elements we need to be alive, for life to exist as we know it. We wouldn't be here but for this process of successive enrichment. We need to have oxygen, we need to have carbon, nitrogen. All of this is predominantly formed in this process of stellar fusion and then explosion. So one natural question then is, if we're going to go hunt for molecules, where should we do it? Where is generically the best place to go look for molecules out there in space? Here's a very nice image of our galaxy. You can see the stars here. There are Magellanic Clouds down here, looking towards the galactic center. And then all of the wispy material in the dark lanes here are dense dust. This right here. So it turns out these are good places if we want to initially go look for molecules, the dense material. And if we zoom in, what we can see is really beautiful images. These are giant clouds of gas and dust. You can see them silhouetted here against the background tapestry of stars. And because they're dusty, they're blocking out some of the stellar light. And so we're not missing stars behind them. It is just that the starlight is being absorbed by the dust, and you're not seeing it in an optical image, such as this. But when people first started looking at these regions, what they realized is that they're, even for space, they're actually pretty low density and temperature. And so all of the traditional expectations of chemistry would say that it would be quite hard to actually form molecules here. And to give you an idea of what the gas conditions are like here in these clouds, you might have a gas temperature that is maybe 10 degrees above absolute zero, so incredibly cold. The total gas density here is maybe 10 to the 4 particles per cubic centimeter. And so just to give you an idea of how rarefied in an environment that is, if we compare that to what the air is around us right now, that's around 10 to the 19 particles per cubic centimeter. So many, many orders of magnitude, many factors of 10 less dense are these clouds. Even though we can see them here blocking out material, they're still very low density compared to the air that we're used to. If you ask what temperature this actually is in terms of things that we're maybe familiar with, it's around negative 440 Fahrenheit. So just very cold and very rarefied. So people looked at this and they realized, okay, that seems like it's going to be hard to actually form molecules. You don't have enough stuff to come together to form molecules, and it's so cold. How are things actually going to happen? But it turns out that we were surprised. So here is a plot of the total number, cumulative number of molecules, distinct different molecules that we've detected in space as a function of year. And you can see for a while, it was pretty close to zero. And then around the 60s or so, what started to happen is astronomers built radio telescopes. And you can see some of the facilities here that are marked with the arrows and labeled. But once astronomers started building radio telescopes, and then they went out and surveyed these giant clouds, they started detecting more and more molecules to their surprise. So after 1965, 1970, the line just goes up, and it continues to go up. And so I think right here, this plot is a little old. It's from 2021. It says the total number of distinct molecules detected is 241. That actually has been updated. It's now around, it's over 300. What's more, I forgot to mention is that the pace of detection is actually increased. So if you just ask how many molecules have been detected over the whole course of modern astronomy, it's around 3.9 molecules per year. If you just ask within the last 20 years or so, it's 6 new molecules. So the discovery pace is actually increasing. The slope of this line is getting steeper and steeper. We're finding more and more. So totally contradicted those very early expectations of no active chemistry and no molecules out there. And to just give you an idea of what some of these are, now don't worry about squinting and seeing each individual molecule, but you can look at these giant tables that identify all of those distinct molecules that went in that other plot. But what we see is a pretty large diversity. You see very simple things that are maybe two, three, four atoms, so relatively small molecules, things that we're familiar with, such as water or CO2, right? Very common, familiar, not exotic at all. But then we also see much larger and much stranger molecules, things that are up to 8, 9, 10, and some that are even quite large, and 60 and 70 atoms. Some of these look like this. They're these very long, unsaturated carbon change. This is a HC 9N. You have 9 carbons just in a line all bonded together. Something like this was very much a surprise. You can't have this on Earth. This would just totally get destroyed, very unstable. But because out in those clouds, the density is so low, once you actually form this thing, it doesn't really hit into other elements and molecules that often. It can actually exist and survive. So that was a bit of surprise to see these weird molecules out there. And as I said, some of them are actually quite large. We're seeing things that have 60 or 70 atoms together. These are fullerenes or buckyballs. If you ask what elements are most common in these molecules, it's the usual suspects. Here is a periodic table where we color the darker the color, that means more of that element has gone into a molecule here. So we see hydrogen, we see carbon, nitrogen, oxygen, sulfur, sort of the usual things, the things that we're familiar with. And by the time you get down to the bottom rows of the periodic table, essentially we don't see molecules with any of those elements in them. Okay, so now that I sort of gave you this broad overview of going out and looking for molecules in space, I want to just walk through a few questions. First, how we actually make these molecules. How do they form? Since that's a fundamental question. How do we actually get this 300 plus molecules out there? How do we detect them as astronomers? How do we use telescopes to find them? And then lastly, and most importantly, give you a few cases where what do we actually learn from them? What is something that we've been able to use these molecules to understand about astronomy more generally? Okay, so first, just to get started, how do these molecules actually form out in space? So, as I said before, here are your ingredients. You have hydrogen, carbon, nitrogen, oxygen, silicon, phosphorus, sulfur. That's most molecules that we detect. These are the building blocks. And so what we need to do is get these different elements, get these atoms together to form bonds. And you can imagine just simply you take element 1, atom 1, A here, and you add it to B, which is another atom or element, and you put that together and you make some bonded molecule called AB. The problem here is that you have a excited state when you do this. Instead of just having a nice stable molecule, you end up with this AB star complex that actually has too much energy in it. And so if you just have this happen, this molecule will actually just fly apart pretty much immediately. It has a lot of energy, it's often very unstable, and it just wants to break back apart to get rid of that extra energy. What helps in a lot of terrestrial chemistry that we're familiar with is you have what is called a so-called third body or three-body reactions, in which once you make this excited state, this AB star, it hits with another body, something that's inert, like nitrogen or oxygen in our atmosphere, and it can just transfer some of that heat away. And then you can end up with a stable compound, AB, and you've then shed that heat to your other inert compound. But the problem is that in space, as I showed before, the densities are really low. It's very hard to do this because the fact just getting 2 things to come together, let alone 3 at the same time, is very improbable. You don't have enough material to rely on these so-called 3-body reactions. And this was one of the fundamental blocks where people thought, really, you can't have all this chemistry because everything's just going to fly apart. Nothing's going to be stable. You can't have these 3-body reactions out in space. But as I said, dust matters. And here's the reason that dust matters. Because those clouds that I was showing you, they're mostly gas, but they're that 1% of dust. And that 1% of dust is really important because it facilitates molecule formation. It turns out that interstellar dust particles like this they actually act as those third bodies. Atoms and molecules will come in and stick to the surface of these dust grains. And they can move around on the dust grain, they can find each other, they can form molecular bonds. And that excess heat, that excess energy can then just be funneled back into the dust particle itself, which the dust particles are much larger than the individual atoms or molecules, very happy to absorb that extra energy and work as your third body in these so-called three-body reactions. So it turns out the overlooked solution here actually was the dust in facilitating this chemistry and this chemical complexity that we see. And people have come up with all these different mechanisms that thus the atoms and the molecules can move around in all kinds of different interesting ways, form all kind of different bonds and molecules. And in fact, there are some folks that put together these very nice models that show an example of this. Here's an example dust grain. And here you have one atom that is now hopping around. And what it will eventually do is it will find its partner and it will get stuck. And then it will form a larger molecule here. So once this spins back around, you'll see the little atom here will get stuck and it will stop moving and it will form a bigger molecule that's then stuck on the dust grain. Yeah, so there it just happened. And now it formed the bond. And then if you have more of these, it's just going to happen over and over. And if it happens over and over, what you get is something like this, just a dust grain that fills up with molecules. You have more and more and more forming with time. We have a lot of time out there in the universe for this just to keep proceeding and coating all of your dust grains with just tons of different molecules. And then the last step in this picture is that sitting out there in these giant clouds that are at first cold. So you have this process, everything's sticking to the dust grains, the molecules are all forming. But at some point, often what you have is a young star that eventually forms out of this material. And once you have a young star forming, you get something like this schematic shown here. The gas temperature increases. All of that molecular material that was ice, that was stuck to the dust, then gets released and it becomes gas. And so once it actually ends up in gas form, that's when astronomers can most readily start detecting it and characterizing it. We can a little bit detect the ice, but it's often much easier once it becomes gas. Once the stars turn on and it becomes gas phase, then we're able to go observe it. So that naturally leads to the next question. How do we actually do this? How do we go out with our telescopes and can say definitively we see this molecule here or this molecule here? So as I said in the beginning, it actually is with the advent of radio telescopes. And so here, when I say radio, I mean anywhere from the centimeter wavelengths to the millimeter or the submillimeter. And this plot here is just showing, if you look at the number, the curves here are just estimates of the distribution of different molecules based on its atomic mass. So if you move more to the right, it's a bigger molecule. If you move more to the left, it's a smaller molecule. But the main takeaway is if you look at the numbers inscribed at the top, you can see that the blue color, the orange color, and the green color, they make up the most number of detections. We've detected most molecules in centimeter, millimeter, or submillimeter wavelengths, and very few at wavelengths like infrared or visible or ultraviolet. So it really is the radio portion of the spectrum that helps us out here. And just quick reminder for those that are less familiar with an electromagnetic spectrum, what we're talking about here is to the far right of the electromagnetic spectrum. This is the region here from microwave to radio where we're detecting most of these molecules, which is why we need these radio facilities. Again, in terms of actual wavelength, this is sort of the size distribution that you should think of, going from the left here, your gamma, X-ray, very high energy, very small, to the much, much longer wavelengths as you move out to the radio portion of the electromagnetic spectrum. And this just maps on, as I said, to energy. As you go here towards the right, you're decreasing in your energy of the photons. Also, this also maps onto temperature. Things that are really quite hot tend to emit things towards to the left, so gamma, X-ray here. And as you move toward the right, those bodies are much cooler. That that emit in the radio part of the electromagnetic spectrum. So why this matters for molecules at all? Molecules want, as many things in the universe, want to be at the lowest energy state that they possibly can be at. And so for them to do this, they need to emit some energy to cool down, to lose that excess energy. And it turns out by having a molecule, by having multiple atoms all bonded together, there is one way for them to do this, which is to change how they vibrate or to change how they rotate. So what they can do is they can go from a fast rotating or a fast vibrating state to a slower state. And in that process, they'll emit that energy, and they'll actually emit it in the terms of a photon, a packet of light. And because these transitions are relatively low energy, where they end up on the electromagnetic spectrum is exactly in that radio microwave portion. So how this actually works in detail is shown here in the schematic. It is essentially just molecules wanting to move slower. They want to spin less rapidly. They want to vibrate less rapidly to give off that extra energy to get to the lowest energy state that they possibly can. And the game that we play here is that if you go in and do all the detailed quantum mechanics, you can't just have any arbitrary rotation or vibration. It is very much like rungs on a ladder. All of these transitions are quantized. They can only happen at very specific rotation rates or vibration rates. And what that means is the amount of energy that the molecule gives off when it changes transitions. Here, when it goes from a faster state to a slower state, they only occur at very, very specific energies. So shown here, they're marked by J here, J3, J2, J1, but these are very specific known rungs on an energy ladder. And if we know the rungs on that energy ladder, we know exactly what wavelength or what frequency of light that's going to be emitted corresponding to one of these transitions. So this is what we do. We know the molecules want to slow down their vibration and rotation. We know exactly what that light will look like, and we can use this to identify and fingerprint different molecules. How this works schematically. So here you have a molecule rotating fast. It wants to get rid of that energy. That's too much energy, so it slows down. In the process of slowing down its rotation, it gives off a packet of light at a very specific frequency. Here, this is the new transition with the wave here that I've annotated. We get that with our telescope, such as this giant single dish radio telescope. What we end up seeing is something like this. We can make a plot of frequency of that light versus the amount of light that we receive. And we'll just see sort of random noise for a while, and eventually this will peak up at a very specific frequency. And that frequency directly corresponds to the frequency of the molecule that was slowing down its rotation, because we get excess light there. We have a lot of molecules making this transition all at the same time. And so that means we get tons of light only at that very, very specific transition. Because these transitions are quantized, they're only happening at only one value. And so if we see that peak, it's a unique identifier that this process is happening. And then what we can do is actually go compare this to what folks in the lab are measuring. They can make some of these molecules in their laboratories. They can measure this spectrum, and they can see exactly where these peaks are supposed to be. And then we can cross-reference our observational data with that laboratory spectroscopy and uniquely identify this has to be this molecule undergoing this very specific transition. And so this is the cycle of identifying molecules out there in space. This is a nice picture, but in practice, it actually is a hard problem to do. Sometimes you get spectra that look like this. So here, same plot. Now you have frequency on the x-axis and you have total amount of light on the y. But when you have very sensitive telescopes, sometimes you don't get one line, you get hundreds and hundreds of lines, often from many, many different molecules, all superimposed on top of each other. So this is sort of the game that astronomers are actually having to do. We get data that's beautiful that looks like this, and then we have to disentangle what molecules are embedded in this spectra. And we haven't figured it out. Something like this probably has, 50% of those peaks are still unidentified. We don't know exactly what they're coming from. But the same principle works. It's just a harder problem. We have to decompose all of this. So it is possible. It just requires some more sophisticated methods. Okay, then lastly, this brings me to what we're able to learn from studying molecular astrophysics. And I want to show you just two quick examples. The first one going back into our gallery of possible ways we can learn about the universe with molecules. The first one is about galactic structure, how we can use this to map out our galaxy in terms of where the molecular clouds are in our galaxy and other galaxies as well. So we often see these really nice artist renditions of the Milky Way structure, where we see all of the spiral arms. We can see the location of the sun here. But these are all inherently reconstructions because we're situated inside of our own Milky Way. We don't get this top-down view. We could never, send a mission this far away to look back at our own Milky Way. So this process, the fact that we can even, reconstruct something like this is inherently difficult because we are embedded inside. It turns out one of the nice tools that we can do this mapping, not the only one, but one of the very nice tools is actually use molecular emission. We would like to do this with molecular hydrogen because, as I said early on, most things are hydrogen. That's where most of the gas is. But it turns out in these giant clouds, most things would be in form of molecular hydrogen or H2. It turns out that it doesn't have a transition we can actually see. It doesn't have a permanent dipole moment, and so we don't actually observe the rotations that it does. And it's invisible at radio wavelengths, unfortunately. So what folks do is they go to the second best thing. The second most abundant molecule out there in our galaxy is actually carbon monoxide. So astronomers are often talking about CO. You'll hear people talk about CO all the time. And that's why, because it's the second most abundant. And so we can use it as a proxy. We roughly know how many CO molecules there are for however how many H2 or molecular hydrogen. So if we see one CO molecule, we just know that there are 10,000 molecular hydrogen. And so we can do this equivalence. But what's nice is we can make beautiful maps like this. Here now is a map of the Milky Way in the CO molecule. So this is carbon monoxide emission throughout the entire Milky Way. All of this done actually with a telescope here from the Center for Astrophysics, the place I did my PhD. It's actually situated in the middle of Boston. It works. It does research grade astronomy despite being in the middle of Boston because it is not optical. It doesn't care about the light pollution. It's fine operating at the radio wavelengths. And so it made this really beautiful map. If we compare this back to that optical image that I showed you before, what you can see is a pretty amazing correspondence with those dark dust lanes. So this sort of circles back to my initial question, where do we find molecules? It's exactly those dark clouds of gas and dust. I could just flip between this for a little bit, but you can clearly see the molecular gas is at the same place where we have these dusty clouds. And what's more is that because when we observe molecules, we actually get a tiny bit more information, and that is the motion. So I won't go into this in too much detail, but because if we measure those spectra, if they get shifted, that line peak, if it gets shifted a little bit, we can actually tell if the gas is moving either towards us or away from us. We get some idea about how the gas is moving. And what that means is when we make these really nice maps using molecular lines, we can actually see how it's rotating. And here is an example of what that has been able to tell us. For instance, we can see the very orderly rotation and spiral pattern. Here, each arrow is the motion of the gas, and each color here is a different spiral arm that has been mapped out in carbon monoxide again. So we get this extra information to even map out structure and motion of the gas. And in particular, from that radio telescope that I had shown a few slides ago, even in the last few decades or so, there's been new discoveries from those mapping efforts. First one being a new spiral arm, one that's very close to the center of the galaxy here, called the 3 kiloparsec arm, as well as the fact that this larger arm here, the Scutum Centaurus arm, goes the whole way 360 degrees around the galaxy. This is mappings that have been done in CO. We can see CO gas going the whole way around here. So this is just one way we can say, use the molecule as a tracer of the underlying structure of our galaxy. Another thing that we can do, because we have this motion, we can see how the gas is actually moving around. we can make full three-dimensional maps of the gas structure. So if we zoom in to the center of our galaxy, called the central molecular zone, shown here, this is our old image, an image from maybe 100 years ago. Here is the new image in 3 dimensions using molecules, where you can actually see that not just the two-dimensional projection, but you can see everything is very filamentary, and you can see the underlying structure. So just a taste of a few things we can do with molecules. It actually isn't restricted to our own galaxies. Here are those really wonderful CO, carbon monoxide emission maps in other external galaxies. So we can look at other galaxies that are not ours and see the very same beautiful spiral structure. We can see where we expect stars to be forming in those galaxies, where the molecular clouds are mapped out beautifully here. Okay, and then in my very last few minutes, I just want to touch on the thing that I study the most, and something that going back to the origins question, which is protoplanetary disks or planet-forming disks. These are the birthplaces of planets. They represent this last stage in the star formation sequence, where you form from your giant cloud, it collapses into a protostar, and you end up with this disk of swirling material before you make a full planetary system like our own. So our own solar system went through this disk phase as well. It looks something like this if you zoom in. Just the details here don't matter so much. Just it's a disk, it's rotating. You have a central star. You have a zone in that disk in the center where you're forming all your planets as all of the material coagulates together and gets bigger and bigger. And this is an active process. This material is either being funneled into the star or into the planets, and this disk is only going to live for a few million years. So all this has to happen really quickly. But the point I want to make is that if we can observe these disks, if we can figure out what the composition, in particular of the gas is, this tells us something about the planets that will form from that disk. So that means the composition of those planets, the potential atmospheres of those planets are all going to depend on what kind of gas is in these young disks. So if we can observe molecules in them, they can tell us something about how our own solar system formed and how other planetary systems are currently forming. And so one telescope that was mentioned in the introduction that I use a lot is called ALMA. And so just very briefly, ALMA is wonderful. It underpins a lot of my and the whole community's research. It's a radio telescope in Chile, and it's great because it's large. It has 66 antennas, which means you're very sensitive to even very faint emission. And it has 5 times the spatial resolution of Hubble because it is so extended. It's essentially 66 antennas working as one giant antenna. Here's just a quick view of a very small portion of those antennas. This is not all 66 of them. But what's really special here is you can take them and you can separate them by more than 10 miles, and then they all work together. So it acts like a 10-mile large telescope. But we can use it in particular for disks. So in disks, we've detected 30 different molecules, including nitrogen, carbon, oxygen, sulfur, all the things that really matter for us that we're used to, all thanks to ALMA. And the very last 2 things I want to just mention is that we have begun to detect that really rich chemical environment in these disks. Maybe 10 years ago, this very first result came out that showed that there were complex cyanide molecules, those that had this CN bond in them. So hydrogen cyanide or HC3N or methyl cyanide, which is the C3HCN, the 3 panels here. And this is a disk. The mission is coming from a protoplanetary disk here. But what was really special about this was that people have suspected that if you have cyanide molecules like hydrogen cyanide, like these other ones, that they have been theoretically shown to represent the first step in forming sugars, amino acids, and even nucleobases. So these are really the precursors to potentially important, biologically important molecules. So the fact that we're seeing those precursors in other protoplanetary disks, in other planet-forming settings, means that life perhaps shouldn't be rare if the chemical ingredients are all out there. And this is a plot from maybe 10 years ago. We have an updated one now from some new ALMA observations in the last few years. Here's 4 protoplanetary disks. The first here is the dust. The middle panel here is where the comets would be if it was our solar system. And then the last row here is different large prebiotically interesting molecules. And you can see that pretty much fills the comet region. You have this rich molecular material throughout the entire region where we expect our own solar system to form in these other protoplanetary disks. So the idea is here we really do have the same ingredients that you need to seed life for other planets found around other stars. And this really calls back to this image potentially that we're seeing something like this going on, where we have our really rich chemistry that's going into these comets that will eventually seed planets that form out of these disks. And so we're really starting to be able to answer these fundamental questions of origins by using molecular astrophysics. And so what I think the future holds, I don't think that this slope of molecular detections is really going to end anytime soon. In fact, I expect that this to only continue. And in fact, I checked a couple of days ago. We already have 3 new molecules discovered in 2025, and we're just starting the year. So that this number of detections per year is really poised to continue, and we're really going to find more interesting and more complex things as we keep going. And I should say that there's a bunch of new telescopes and new upgrades that will happen. And every time that happens, you see a little uptick in this plot. And so we're really poised to continue to break open a new discovery space in astrochemistry. So I'll end there and really just say that there's a bright future for using astrochemistry to understand the cosmos, our own origins, astrophysics broadly. And so I say thank you for the attention, and I'm very happy to take any questions.
All right. Thank you so much. Feel free to unmute yourselves if you can.
Mhm.
And I thank you, Charles. That was a rich brew of of molecular phenomenology. Oh, we have a question from Bill Wall. Why don't we go with you, Bill?
Right, thanks. So, yeah, I really enjoyed your talk. It was nicely organized, nicely explained. My question is a question that's been in the field for a long time, and maybe there are good answers to this now, or better answers than there were. I mean, the first stars formed in presumably in molecular gas, but how did the molecular gas form if there was no dust, which came from the stars? So there have to be other mechanisms for forming molecules, and one mechanism I believe is you have an H atom and an H minus come together and form hydrogen H2, but the electron shoots off. That's one mechanism. There are probably a whole bunch of these that work out. So what do you say to that?
There are, yeah, there are other sort of alternate ways to do this when you don't have dust facilitating. They are just not competitive in environments when you have dust. So the moment you have dust, then you start favoring those routes. But like you said early on, when you don't have lots of dust, then yes, you have to appeal to other slower mechanisms because they're the only thing you have. So it's just an efficiency argument. The most efficient thing in early time doesn't involve dust, but the moment you have dust, then things transition away from that, which also
Right, but then
accelerates the growth of chemical complexity because early on you're sort of at a bottleneck, and then eventually you start getting dust, and then it goes quite a bit quicker.
yeah, and then there's the issue of what's a large molecule and what's dust? Like are pause molecules or are they dust? And then how do you form those molecules? Those molecules, I assume, are formed in stars, or maybe it's because they're just photodissociated from in the interstellar medium. So then how do you have to distinguish between how molecules form and how dust forms? And then there's this boundary between the two. So how do you address that?
That's an excellent question. There's not a hard cutoff for what a molecule and what a dust or PAH is. I definitely agree. And we are addressing that now. I think there is not consensus in the field about either top-down or bottom-up chemistries, particularly for the PAHs. But it is something that now folks have actually been able to detect individual PAH molecules in the gas phase in some of these clouds. And so they're going from being able to actually detect single ring, double ring, even triple ring aromatics. And so I think that is going to be the solution to be able to actually detect individual PAHs, do the necessary chemical modeling, and then figure out, or is
Right,
it just big dust being broken down, or is it building up from simpler things?
right. Okay, thanks.
So Charles, could you stop sharing your screen so we could get everybody
Yes, sorry,
present?
is
That
that
would be
better?
great. Um, so we have a question from Gregory McNiff. You'll have to unmute, Gregory.
Uh, oh yeah, thank you. I apologize for the background music. Definitely echo the comment about it being a great talk. Just one clarification question. Um, you talked about the 2 lightest elements, I think helium, hydrogen. I also wonder if lithium would fall into that category. And then on the particular light bursts, you mentioned we can measure them at a specific wavelength. Is that every molecule emitting that light burst, or do specific molecules emit specific lights at specific wavelengths? Apologize, I'm not articulating that properly, but how
No,
precise can
that
you
makes
be
sense.
about knowing? Yeah.
Yes, great questions. Yes, you would absolutely have lithium as part of the Big Bang nucleosynthesis process. It would be trace. It would be a very small fraction. So yes, it is there. It's just not anywhere near as abundant as hydrogen or helium. So absolutely. And to your second question, yes, every molecule is going to have its own individual spectrum. And sometimes that will peak in the radio, sometimes that will peak more towards the microwave, and it will shift around. It depends in detail on the molecular structure and which sort of degrees of freedom that molecule has. Something I didn't touch about is that there's a whole vibrational spectrum as well. So you actually get rotations, vibrations, and that spectrum goes from the radio the whole way out into the infrared a bit. So you see more vibrations in the infrared. So absolutely, everything is very distinct. And that actually is good. That helps us disentangle things. If everything was all sort of emitting at the same region, it would be a big problem.
Perfect. Can I ask one or two more follow-ups? You talked about the density at the center of the galaxy. Is there any relationship between a black hole and molecule formation? And then on the ALMA telescope, I think it works on the principle of interferometry. Apologize, I'm not pronouncing that right. Why don't we just make a huge radio telescope, even much larger than the one we have? Would that give us any more precision?
Yes. Okay. First question about black holes. Not particularly, because once you actually have a black hole in that kind of really harsh environment, you destroy a lot of your molecules. It doesn't really facilitate growth of molecular complexity. It more destroys it, unfortunately. In terms of the radio telescope, yes, that is an aim. That would be wonderful to make a bigger and bigger one. They're hard. They're difficult to do. I see a comment about, yeah, EHT, the Event Horizon Telescope, which did look at our own black hole as well as another black hole, was the size of the Earth. It used a string of radio telescopes throughout the entire world. We need also sensitivity because what we're looking at is pretty faint. And so if you start stretching out your array, your sensitivity tends to go down. So you need to put a lot of dishes. So it would be wonderful to have like a 10,000 antenna based telescope across the world. That costs a little bit. There's a new proposal for a next generation, very large array, NGVLA, which would be continental size, go from Mexico to Canada. And that's sort of the next thing on the future in the next 10, 15 years. So like an upgraded ALMA, but in the Northern Hemisphere.
That's great. Thank you very much, Professor. It was a great talk.
I think we'll go with Mike Prim before Mike Deneen.
Okay, great. When it comes to these, as you've been working up the towards larger molecules, I would presume with larger molecules that there's got to be a combinatoric explosion around the lines that the different modes that the molecule can emit. How much is, I mean, to what degree is that limiting your ability to detect larger molecules, or you get into instrument issues in terms of how precise, how small the buckets and the frequencies need to be in order to discriminate? What do you think is the limiting factor on being able to sense larger molecules?
Yeah, great question. I get two things. One would be the laboratory spectroscopy, actually. We don't know the spectra well. Like complex spectra with lots of features are good because we have lots of techniques like cross correlation and things where the more complexity we have, that actually helps us if we know it, if we know the structure. The moment we don't know the structure, then it is a huge problem and then it starts contaminating everything. So having laboratory data matters quite a lot, and that's harder to do for these more exotic and larger molecules. But people are working on it. The second thing is just signal. Some of these very large molecules have very, very faint features. And so you need to spend hundreds, thousands of hours of telescope time to pick them up. And so they're just buried in the noise until you do that. So it's both those things I think are the big limiters right now. Complexity is actually okay. Complexity actually helps us if we can understand it.
Great. Thank you.
Monsieur Deneen?
Yeah, real simple thing. I just, something in me shouted, what's the sample size when you were doing CO and hydrogen linking? So I was wondering if you could do a short outline of why those two are linked necessarily in nature, not in observing, but in nature, so that you can rely on that pairing.
Yeah, that's a really wonderful question that hints on lots of deeper things. The first order answer to that is it is just density. That if there is a lot of gas somewhere, you see a lot of molecules, everything. You see a lot of H2 and CO and all the other molecules. They all are just in the same place because they're all set by first order density. In detail, this factor, this conversion factor is called the XCO factor. It's not constant. There are lots of things that actually go into it. And so when people are doing these models, they actually have to consider the physical environment because the ratio is not always constant and you want to correct for that. And we do understand why the ratio gets changed. But it is an important and it probably adds the most uncertainty in doing this sort of comparison. We do it because we have to, not because we want to. We'd love to observe molecular hydrogen when we can. But yeah, that's a really deep question. That's an excellent question.
All right, thank you.
I'm going to butt in here and ask a question having to do with the molecules that are found in the molecular clouds and cloud cores versus the molecules found in these protoplanetary disks. Can you imagine what sort of chemical pathways might lead from one to the other?
Oh, yes. So this is something broadly that we consider inheritance, something that's called inheritance. And so it is just the chemistry that happens early on in the molecular clouds, all the ice chemistry, just gets inherited into the protoplanetary disk because the disk forms from the molecular cloud. It's the same material that makes up the disk. And so one idea is that that material just is the same. It just gets incorporated into the disk. Nothing has really changed. Whatever you see in the molecular cloud is what you see in the disk. That is probably true for some fraction and some types of molecules that you can imagine that the process of making a protoplanetary disk, of making a protostar, is very energetic. You get hot gas, you actually should change some of the underlying chemistry. And so it's this competing process. How much do you just inherit? How much do you change as you form? And that is a fundamental open question that remains. We're trying to stitch those together. And you can only do it by having detailed observations and models of your clouds, and then detailed models and observations of your disks, and then comparing them.
Thank you. Bill, Wall?
Yeah. When you're talking about life now, I mean, I was just checking online. There are papers on the microwaves, or at least trying to get a microwave spectrum of, let's say, DNA. Those papers I found are old, but maybe a bit of researching can find something new. So, what do you say about that? What's the latest on the microwave or millimeter wave spectrum of DNA?
Yeah, oh, that's a good question. I don't know the details of that. But in terms of detecting something that large and that complicated, it's very unlikely we'll have the signal to do that within the next many decades. I think we're at that point, you're really signal limited. And so we're never going to be able to do that in a protoplanetary disk because there's just not that much material. In the giant molecular clouds, you're integrating through a line of sight with tons of material. Even if it's dense, you have huge, area to integrate from. And that's where all the most complex stuff has been found in these giant molecular clouds because you just have so much area to integrate through. Even there, we are not anywhere close to sort of DNA level of complexity, unfortunately. And we may never be there until we have sort of the next leap in technology.
But what about observing solar system objects, for example?
That might be possible. Yes, if you can find bright features in solar system objects, at that point, maybe in situ is better. Also, you just send a probe, but that would be probably the only thing that's feasible. Close, bright, abundant. I don't
Thanks.
know about the abundant part, right? That's the issue, right? It have to be abundant. We don't know of any other
Well,
sources that are
yeah,
abundant.
we all want to know about the abundance issue.
Yeah.
All right. Do we have any other questions?
Well, I posted a longer one. Since you're interested in uh, protoplanetary disks and so forth, it was occurring to me while we were talking how these larger, heavier molecules might actually promote the ability of the kind of the early forming hot, messy planets to actually retain these materials, even if those materials were later reorganized into gases like nitrogen or water vapor or carbon dioxide and so forth, just for no other reason than because of the fact that they're heavier and all things being equal, that means a lower average velocity at a given temperature. What sort of things have you guys gotten into? I'm an exoplanet guy by my nature, so this is you're on the front end of the cool stuff I like looking at on the back end.
Yeah, no, that's a great question. Yeah, no, I can tell. Like, sort of, exoplanet as far as we care about the heavier things. That makes sense. Broadly, the process is so hot and so energetic. We really don't expect a lot of the primordial stuff to be around, even if it's modestly heavier. It's still probably not going to survive in its form. And so that's why the scenario I was showing was more of cometary delivery, because
Mhm.
that is a more reasonable route to deliver this prebiotic stuff when you have a cooled down planet. Early on, you're probably really just wiping out most of this.
That was kind of where I was kind of leading, is I wasn't sure if, like I said, I know you mentioned about the grazing, if you will, or the seeding indirectly. But what I wasn't sure about is if there were other mechanisms for that primordial nature to be retained, at least until the it was delivered onto the forming body, so that gravity has a chance to grab a hold of it, if you will, or something along those lines.
Yeah, I mean, this will in detail depend on timescales, how fast actually planets form and cool. But I think the most plausible route is the cometary delivery one, rather than, I mean, you could imagine maybe you have a very long-lived disk that, planet clears out its space really quickly and is able to cool, and then some stuff moves in. But I don't know if that's going to be the dominant mode for this.
Great, thank you.
But we can test. We can test this. We're in the process, I guess, of testing this. How long these things live, and with the exoplanet, the spectra from like JWST, we'll see the degree of complexity that does exist, and that should tell us something to feed back into the disk work.
Great, thank you.
All right. Well, I hope you enjoy your rich desserts made of all kinds of sugars and amino acids. And so I wish you all well. This was wonderful, Charles. Um, it makes you appreciate what we have here, um, and just marvel at what might be going on in these crucibles of creation.
Well, thank you so much for having me, and thank all of you for spending a Friday night together. Hopefully, this was interesting to everybody.
Thank you very much. It was great.
Yes.
Thank you.
Okay,
All right,
thank you all.
take care.
Take care, Bill.
You
Thanks,
too.
Bill.